Welcome to the 7th lecture of module 2 on mass transfer operation. Before going to this lecture, let us have a brief recap on our last lecture. We have started with interface mass transfer and we have discussed the fundamental concept of interfacial mass transfer. We considered major component over here is equilibrium between the phases, and then we considered Raoult's law, and the third thing we considered is Henry's law. We will continue our discussion on interface mass transfer. In this lecture, we will consider Lewis and Whitman two film theory for the mass transfer between the phases. Lewis and Whitman proposed this theory in 1924 for the interface mass transfer, or it is known as two film theory. Here the following things has been considered. Two stagnant film exist on either side of the film. So, first thing is considered two stagnant film. So, note that the films are considered as stagnant on either side of the film or either side of the interface. Mass transfer occurs through the film in sequence. Mass transfer within the film by molecular diffusion only. So, molecular diffusion occurs within the film. Bulk phases are considered well mixed, and beyond this the film's concentration in a phase is equal to the bulk concentration. So, beyond the film, that is both gas side film as well as the liquid side film, beyond these films the gas phase or in the liquid phase both are considered now well mixed, and the concentration which will reach there is the bulk concentration of that component in that phase. Equilibrium at interface. So, these are the things or assumptions considered under Lewis and Whitman theory, which is proposed in 1924. But no, in reality there is no evidence of the film. So, which we could not see the film exist between the phases, and it is impossible to estimate the film thickness, very difficult to measure the film thickness. So, the transfer mechanism which are proposed is, you can see this is bulk, gas bulk, and this is the liquid bulk, and liquid bulk is considered as turbulent liquid bulk, gas bulk is considered turbulent gas bulk, and this is the interface. So, this is interface, and on the liquid side there is a laminar liquid film which is the thickness is considered as delta L. In the gas side there is also laminar gas film which is considered as delta Z. There is a flux, gas is absorbing, and we consider the solute A is diffusing or is transferring from the gas phase to the liquid phase, and in the film the diffusion or mass transfer happens through molecular diffusion or molecular flux. You can see the concentration at the bulk is YAB and concentration at the interface is YAI in the gas side, and the liquid side is XAI and the liquid bulk is XA. So, the three step transfer which we already discussed over here, the bulk gas phase, to the gas side interface. Gas side interface, then it transfer or transfer through the interface. So, it goes to the liquid side interface. So, that is the interfacial transfer. Then liquid side interface to the liquid film, through the liquid film it goes to the liquid bulk. So, these are the three transfer steps generally involved for transfer of the component from the gas phase to the liquid phase. Now, Na is the flux, and if Ky is the mass transfer coefficient in the gas phase based on the mole fraction unit Ky, which into the driving force in the gas phase, that is YAB minus YAI, that is the bulk concentration over here, and YAI which is over here. So, this is the driving force into the mass transfer coefficient in the gas phase. Similarly, in the liquid phase, it will be the flux would be equal to Kx is the liquid side mass transfer coefficient into the concentration gradient, that is concentration of component A at the gas liquid interface, that is Xai would be higher than the bulk concentration of that solute in the liquid. So, the driving force is Xai minus Xab. So, the bulk concentration, and this, since there is no resistance at the interface or interface is at equilibrium, it is considered instantaneous transfer, and hence we can write the flux of the both phases would be equal. So, that is related with this relation. Now, here Xai and Yai are related by the equilibrium relation. So, equilibrium relation is Yai is equal to function of Xai. So, the interfacial concentration, as we considered in the Lewis and Friedman theory, there is equilibrium at the interface. So, Yai would be function of Xai. If we rearrange this relation, then we can get Yab minus Yai divided by Xab minus Xai would be equal to minus Kx by Ky. Consider all these parameters which are in small x and small y term. So, there is a typo. So, slope is minus small kx by small ky, and the driving force in the gas side, you can see the gas side driving force is Yab minus Yai. So, this is the gas side driving force, and this is the liquid side driving force. So, if we consider this relation where Yab and Xab, these are measurable quantity, whereas Yai and Xai is not measurable quantity, because these are interfacial concentration. So, it is very difficult to measure this interfacial concentration. If all these are available, then easy to calculate the flux. So, if I can calculate the interfacial concentration Xai and Yai, then it would be easy to use this flux equation to calculate the flux. But these equations is not helpful for mass transfer calculation, because the interfacial concentration is not known to us. So, we have to depend on the measurements to calculate the flux, and it is possible to measure experimentally the bulk concentration. So, if we can relate the flux equation with respect to only the bulk concentration or the measurable quantity, it would be easy for us to calculate the flux. So, as we said, it is quite difficult to measure the interfacial concentration. So, what to do in that case? Since the concentration gradient takes place over a extremely small distance, very small distance, it is the ordinary device cannot measure the interfacial concentration. Because of this reason, this theory is impractical and which lead to follow some alternate method. Now, if we consider at steady state, what happens? The Na we can write Ky into Yab minus Yai would be equal to Kx Xai minus Xab would be equal to capital Ky into Yab minus Ya star, because our transfer is happening from the gas phase to the liquid phase. So, if we can get the equilibrium values, the overall driving force from the gas phase to the liquid phase is from Yab to Ya star. So, that is why we can write. So, this capital Ky include the mass transfer coefficient both in the gas phase and in the liquid phase, or the resistance involved in both the phases. So, from this relation we can just rearrange this equation. We can write from here is Xai minus Xab by Na, which we can write 1 by Kx, and Yab minus Ya star divided by Na. From this we can write, and this we can write Yab minus Ya star by Na would be equal to 1 by capital Ky. If we look into this figure, Yab minus Ya star, that is this one and this one, would be equal to Yab minus Yai. So, the distance from here to here plus Yai minus Ya star. So, this distance and this distance. So, if we just rearrange Yab minus Yai plus, if we multiply both numerator and denominator by Xai minus Xab, and this will be Yai minus Ya star divided by Xai minus Xab into Xai minus Xab. From the figure we can see Yai minus Ya star divided by Xai minus Xab, that is from this. So, this represents the slope of this line. So, which is m dash. So, we can write Yab minus Yai plus m dash Xai minus Xab. Now, Yab minus Ya star by Na would be equal to Yab minus Yai divided by Na plus m dash Xai minus Xab divided by Na. From this we can write this is equal to 1 by capital K, and this is 1 by small ky, and this is 1 by small kx into m dash. So, 1 by ky, capital Ky would be equal to 1 by small ky plus m dash by kx, small kx. So, this is if we get the overall mass transfer coefficient. So, this is the relation between the overall mass transfer coefficient and the individual mass transfer coefficient, that is mass transfer coefficient in each phase, and this is basically in terms of the resistance in series model. So, 1 by capital Ky is the overall resistance for the mass transfer from the gas phase to the liquid phase. 1 by Ky is the gas phase mass transfer resistance, and m dash by Kx is the resistance in the liquid phase. Now, alternate method based on the bulk concentration. Equilibrium distribution curve for a system is unique at a particular temperature and pressure. So, because once the temperature and pressure is specified and we can get the equilibrium distribution curve at that temperature for a particular system. So, Y A star is in equilibrium with X A B. This X A B would be in equilibrium with the equilibrium concentration, that is Y A star. So, we can write flux N A would be equal to capital K Y into Y A B minus Y A star. So, this capital K Y is the overall gas phase mass transfer coefficient. Now, similarly, in case of the liquid phase, we can write X A star is in equilibrium with Y A B. So, we can write N A would be equal to K X, X A star minus X A B, and this capital K X is the overall liquid side mass transfer coefficient. So, we can define the flux with respect to the measurable quantities, that is the equilibrium concentration and the bulk concentration. Now, how to obtain relation between the overall coefficient and individual coefficient? We have already discussed before the relations or derived the relations between the individual mass transfer coefficient and the overall mass transfer coefficient, and this can be possible only when the equilibrium relation is linear. So, if the equilibrium relations is linear, then only we can relate with the overall mass transfer coefficient, like Y A I would be equal to m into X A I, and it is valid at low concentration where the Henry's law is obeyed. That means, m is equal to h by partial pressure, okay, of that component. So, Y A star would be equal to m X A, and we can write Y A is equal to m X A star. Now, from the same relation we can just rearrange from this figure. N A is equal to K Y, Y A B minus Y A I is equal to K X, X A I minus X A B is equal to capital K X, X A star minus X A B. So, we can rearrange this X A star minus X A B by N A would be equal to 1 by capital K X. So, similarly, like earlier case we have derived, we can write this relation X A star minus X A B would be equal to X A star minus X A I from this figure in the liquid side plus X A I minus X A B. Now, if we multiply both numerator and denominator with Y A B minus Y A I, then we can write X A star minus X A I divided by Y A B minus Y A I into Y A B minus Y A I plus X A I minus X A B. So, this ratio is the nothing but over here you can see is m double dash. So, m double dash is Y A B minus Y A I into divided by X A star minus X A I. So, we can just substitute over here and we will obtain Y A B minus Y A I divided by m double dash plus X A I minus X A B. So, from this relation we can just write the equation of individual mass transfer coefficient and overall mass transfer coefficient based on the liquid phase mass transfer coefficient. So, overall mass transfer coefficient based on liquid phase, that is 1 by capital K X would be equal to 1 by m double dash K Y plus 1 by K X. If it obeys Henry's law, then the equilibrium line is straight and this m dash would be equal to m double dash equal to m. So, in that case we can write 1 by capital K G would be equal to 1 by small k g plus h by k L. So, when the equilibrium line is straight, in that case these relations will be valid. M dash would be equal to M double dash would be equal to M, and we can get the relation between the overall gas phase mass transfer coefficient Kg would be equal to 1 by Kg, capital Kg would be equal to 1 by small kg plus h by small kl. Or similarly, we can write in terms of the overall mass transfer coefficient in the liquid phase a capital KL, that is 1 by capital KL would be equal to 1 by h small kg plus 1 by small kl, that is individual mass transfer coefficient liquid phase, and this is individual gas phase mass transfer coefficient, this is overall liquid phase mass transfer coefficient. Now, consider case 1 where h is small, that is Henry's constant is small. From the earlier equations we can write 1 by capital Kg would be 1 by small kg. That means gas film absorption main resistance is the main resistance, that is ammonia in water or HCl in water. In that case what will happen, the resistance will lie in the gas phase only, but not in the liquid phase. If H is large like SO2 in water or carbon dioxide in water or oxygen in water, that means the affinity of these components sulfur dioxide, carbon dioxide or oxygen in water is very less. So, you have a very high H value. In that case what will happen, 1 by capital KL we can write is equal to 1 by KL, small kl, that is liquid film absorption is the main resistance. So, 1 by Ky would be equal to Ya minus Ya star by Na. If we can just get the gas side mass transfer coefficient, we can just calculate the flux. Now, from the geometry of the figure we can write once again, it is Ya minus Ya star is equal to Ya minus Yai plus Yai minus Ya star. So, we can rearrange, it is 1 by small ky would be equal to Ya minus Ya star divided by Na, which is equal to Ya minus Yai divided by Na plus Yai minus Ya star divided by Na, and we can write Ya minus Yai divided by Na plus m into Xai minus Xa divided by Na. Now, we know that Na is equal to Ky Ya minus Yai would be equal to Kx Xai minus Xa. So, from equation 1 and 2 if we just correlate among them, then we can get 1 by capital Ky would be equal to 1 by small ky plus m by Kx. Similarly, in case of the liquid phase we can obtain in the similar manner. So, 1 by Ky is the individual gas phase mass transfer coefficient, m by Kx is the individual liquid phase mass transfer coefficient, 1 by capital Ky is the total resistance of the two phases, and 1 by small kx is the individual liquid phase mass transfer coefficient, 1 by m ky is the individual gas phase mass transfer resistance. Now, the fractional resistance offered by the gas phase we can write or we can define is the resistance offered by the gas phase divided by the total resistance of the two phases. So, the fractional resistance would be 1 by small ky divided by 1 by capital Ky. Similarly, in case of the liquid phase, the fractional resistance offered by the liquid phase we can write resistance offered by the liquid phase divided by the total resistance of the two phase. So, this is equal to 1 by m small kx divided by 1 by capital Kx. Now, let us take an example for gas absorption of certain gas from an air stream by water, the value of Kg was found as 2 into 10 to the power minus 6 kilomole per meter square second kilopascal. The absorption takes place at 298 Kelvin and at 1 atmosphere pressure. At a particular location of the column, the gas phase concentration is 5 mole and the liquid phase concentration is 0.2 mole percent. Only 10% of the total resistance lies in the liquid phase. So, it is given only 10% of the total resistance lies in the liquid phase. The solution obeys Henry's law and the value of Henry's law constant m is given as 1.5 at the temperature and pressure conditions mentioned. Now, we need to calculate the individual mass transfer coefficient, flux and interfacial concentration. So, Kg is given over here, which is 2 into 10 to the power minus 6 kilomole per meter square second kilopascal. So, Ky is Kg into Pa, which is equal to Kg is given and Pa is 1 atmosphere, which is 101 in 0.3 kilopascal. So, this is coming out to be 2 into 10 to the power minus 6 into 101.3, which is equal to 2.03 into 10 to the power minus 4 kilomole per meter square second. Now, since the 10% of the total resistance is lies in the liquid phase and hence, so 90% of the total resistance should be in the gas phase. Now, we know that the fractional resistance offered by the gas phase is equal to 1 by small ky divided by 1 by capital Ky. So, it would be capital Ky by small ky. So, this ratio of the mass transfer coefficient, that is overall mass transfer coefficient divided by the individual mass transfer coefficient based on the gas phase. And now, if we just put the values which is 90%, so it will be 0.9 would be equal to capital Ky by small ky, and so small ky would be equal to capital Ky by 0.9. So, capital Ky we have calculated here, which is 2.03 into 10 to the power minus 4 divided by 0.9. So, we will have 2.26 into 10 to the power minus 4 kilomole per meter square second. So, Ky small ky is now calculated. Now, fractional resistance offered by the liquid phase, we know it is m by small kx divided by 1 by capital Ky, which is equal to m capital Ky divided by kx. So, as we know the values of capital Ky and m which are given. So, and also the fractional resistance offered by the liquid phase we know. So, we would be able to calculate small kx. So, 10% resistance which lies in the liquid phase would be equal to m ky divided by kx. From there we can write m by kx would be equal to 0.1 by ky. So, now we know that 1 by capital Ky would be equal to 1 by small ky plus m by kx. So, this is the resistance in series models. We can correlate with the, as you have learned, the overall mass transfer resistance is related with the individual mass transfer resistance of the films or the phases. If we just rearrange this equation, m by kx would be equal to 1 by capital Ky minus 1 by small ky. So, this would be equal to, so as we know from here m by kx is equal to 0.1 divided by capital Ky. So, we can substitute over here this part would be equal to 0.1 divided by capital Ky. So, from here we can write Kx would be equal to m capital Ky divided by 0.1. So, if we substitute the values, which is m is 1.5 into 2.03 into 10 to the power minus 4 divided by 0.1. So, this will give 3.045 into 10 to the power minus 3 kilomole per meter square second. So, this is the individual mass transfer coefficient in the liquid phase, and we have also calculated the individual mass transfer coefficient in the gas phase. So, this part we have done. Now, we have to calculate the flux and interfacial concentration. Now, the equilibrium relations Y A star would be equal to m into x A. So, m is 1.5 into 0.002 because it is 0.2 mole percent which are given over here. The liquid phase concentration is 0.2 mole percent. So, it is 3 into 10 to the power minus 3. So, we can calculate the flux is equal to capital Ky into YAB minus YA star. So, YAB is given, gas phase concentration is 5 molar, and so it is 0.05, capital Ky is known 2.03 into 10 to the power minus 4 into 0.05 minus 3 into 10 to the power minus 3. So, if you substitute the values over here and this is 0.05. So, we will be able to obtain 9.54 into 10 to the power minus 6 kilomole per meter square second. So, this is the flux which we can calculate. Now, Na, the flux is equal to small ky into YAB minus YAI. So, we have to calculate the interfacial concentration. YAI is the concentration of gaseous solute at the gas liquid interface. So, from this equation we can write YAI would be YAB minus Na by small ky. This is 0.05 minus 9.541 into 10 to the power minus 6 divided by 2.26 into 10 to the power minus 4, and from there we can calculate it is 0.05 minus 0.042 and which is equal to 0.0078 mole fraction. So, the interfacial concentration is 0.0078. Now, similarly for the liquid phase concentration we can correlate with XAI would be equal to YAI by m. So, m is the Henry's law constant. As you know, the gas liquid interface we can correlate with the Henry's law constant to calculate the interfacial concentration. So, if we apply that, this would be 0.0075 divided by 1.5. So, it is about 0.0052. So, to cross check the flux with this, if we use the interfacial concentration in the liquid phase, which is Kx into Xai minus Xab, we can write the bulk concentration is 0.002 and the Kx is 3.045 into 10 to the power minus 3, and then the interfacial concentration which we have obtained over here we can substitute, we will get the values of the flux and which is 9.744 into 10 to the power minus 6 kilomole per meter square second. Hence, the values for the flux which we have obtained using the interfacial concentration is same as based on the overall mass transfer coefficients. So, the calculation is correct. So, finally, we are able to calculate the individual coefficient flux and the interfacial concentration. So, now we will move to contacting devices where the mass transfer takes place between the gas and liquid phase, and we try to do the material balance for the component which is transferred and try to generate the operating line. In general, two phases are in direct contact in conventional mass transfer equipment. In case of a flow process, due to transfer of solute from one phase to the other, the concentration within each phase changes as it moves through the equipment. So, for a batch process, concentration in each phase changes with time, because once the absorption happens batch wise, then the concentration in the gas phase as well as liquid phase changes. If the concentration changes during the process, then what happens? It produces the variation in the driving force. Since the driving force is also changes, this can be followed with the help of material balance, how the concentration driving force changes for the mass transfer, and which will give us the operating line. Three modes of operations happens generally in the industrial equipments. One is counter current operation, and then co-current operation and cross current operations. Let us consider counter current operation. This is a column in which there is a inlet gas, and at the bottom of the column, and then inlet liquid at the top of the column, and then outlet gas at the top of the column and outlet liquid at the bottom of the column. So, here L is the rate of liquid flow at any arbitrary location in mole per time. So, L is the rate of liquid flow at arbitrary location in mole per time. This small x1, x2 and x. So, x1, x2 and x at any location. These are the mole fractions of solute in liquid phase at respective locations. Capital X1, X2 and X, capital X1, capital X2 and capital X, which is over here. These are mole ratios in liquid phase at respective locations. G1, the rate of gas in at location 1. So, G1 is the gas flow rate at location 1 in mole per time, and G2 is the gas rate, gas out at location 2, rate of gas out at location 2. So, the bottom of the column is considered, or the location at the bottom is considered as 1 and top is considered as 2. Now, Gs, the rate of gas flow on solute free basis, which is defined over here, Gs on solute free basis. So, it does not change when passes through the column, that is the inert for the absorption process or for the mass transfer. So, Gs is the rate of gas flow on solute free basis in mole per time, and G is the rate of gas flow at any arbitrary location. So, which is given over here. Small y1, y2 and y are the mole fraction of the solute in the gas phase at respective locations. And capital Y1, Y2 and Y are the mole ratios of the solute. L1 is the rate of liquid at location 1, and L2 is the rate of liquid in at location 2, and Ls is the rate of liquid flow on solute free basis in mole per time. We should know the relations between small y and capital Y, small x and capital X. Basically capital is mole ratio unit, that is on solute free basis, and small y is the mole fractions unit. So, the relations between capital Y and small y is that capital Y is equal to y by 1 minus y. That means, the solute which is excluding the solute, it is on solute free basis. From this relation we can rearrange 1 plus y would be equal to 1 plus y by 1 minus y, which would be equal to 1 by 1 minus y, and from there we can write 1 minus y would be equal to 1 by 1 plus y. So, from here we can write y would be equal to 1 minus 1 by 1 plus y, and we can get the relations between small y and capital Y, which is capital Y divided by 1 plus y. So, this relation we should remember while defining mole ratio and mole fractions unit, or while changing this parameters. So, the Gs, which is the gas flow rate on solute free basis, we can write the total gas flow rate divided by 1 plus y, and capital Y as we said is y by 1 minus y, small y would be equal to capital Y by 1 plus y. Similarly, Ls would be L divided by 1 plus capital X, and capital X would be equal to x by 1 minus x, and small x would be equal to capital X divided by 1 plus x. So, based on this conversion term, we can develop an envelope for we can do the overall macroscopic mass balance for particular component A over the envelope 1. So, the envelope 1 considered the whole column over here, and if we write if we take the assumptions, that is there is no chemical reaction. So, in that case the total moles of A entering would be equal to the total moles of A leaving. So, we can write G1 Y1 which is entering plus L2 X2 would be equal to G2 Y2 plus L1 X1. So, entering moles would be equal to exit moles. If we do the component balance over envelope 2 over here and taking at any location, so we can get G1 Y1 plus Lx would be equal to Gy plus L1 X1. This is equation 2. Now, in terms of the solute free basis, equation 1 can be written as G1 into y small y1 we can substitute with capital Y1 divided by 1 plus y1 plus L2 into x2 capital X2 divided by 1 plus capital X2 would be equal to G2 capital Y2 divided by 1 plus capital Y2 plus L1 capital X1 divided by 1 plus X1. So, we substitute the conversion terms between small x and capital X, small y and capital Y. Now, if we write, so this is basically Gs G1 by 1 plus y1 we can write Gs y1 plus Ls x2 would be equal to Gs y2 plus Ls x1. Now, from here if we just rearrange, we can get Ls by Gs would be equal to y1 minus y2 divided by x1 minus x2. So, this is equation 3. We can see it is a equation of straight line. In the xy diagram, which passes through the points x1, capital X1, capital Y1 and capital X2, capital Y2 with a slope Ls by Gs. Now, equation 2 can be written on solute free basis. This if we write in terms of solute free basis, we substitute the terms, it will be G1 Y1 by 1 plus Y1 plus L into capital X by 1 plus X would be equal to G into Y by 1 plus Y plus L1 into capital X1 divided by 1 plus X1. So, from here we can write Gs into capital Y1 plus Ls into capital X would be equal to Gs into capital Y plus Ls into capital X1. So, if we rearrange, it will be Ls by Gs would be equal to capital Y1 minus capital Y divided by capital X1 minus capital X. So, this is a equation of straight line that passes through the points x1, y1 and xy with a slope Ls by Gs. This equation 4 as you can see it passing through any point inside the column xy, any points. So, the equation 4 is a general expression relating to the bulk composition of the two phases at any location with the terminal composition. Thus, this equation defines the operating conditions within the equipment and hence is called the equation of operating line. Okay. So, the equation 4 is the equation of operating line. So, this is the equation and you can see when there is transfer from the solute from the gas to the liquid, the slope of the curve is this, that is between m and n. If you plot, so you will get the slope of the curve is Ls by Gs, and similarly if solute transfer from the liquid to the gas, your slope of the curve you will get between these two, which is below the equilibrium curve. Now, it is important to note the difference between the equation 2 which is based on the mole fractions unit and equation 4 which is the mole ratio unit. When written in solute free basis, the operating line is straight because the mole ratios are based on the constant quantities Ls and Gs. So, when we write equation 4, it is on solute free basis, the operating line are basically straight line because it is based on the constant quantities Ls and Gs. But on the other hand, the quantities G and L which is no variable inside the column, it is changing because of the solute transfer between the phases. As the solute transfer from the gas to liquid, L will gradually increase and gas will gradually decrease. So, the slope of the operating line L by G will keep changing. The operating line will no longer be straight line, but if we consider very dilute solutions, in case of the concentration of the both phases are very low, then the operating line is nearly straight and we can consider straight line. But if it is not straight, it looks like this, the operating line will be curved like this. Okay. So, this is the operating line when we write in terms of the, this is small y mole ratio unit, and when the concentration changes between the phases are high, in that case this is not the straight line, the operating line is not the straight line, it is a curved line. So, if we look into the overall mass balance of component A over the envelope, this is the envelope for co-current operation. We have done for the counter current operation. If we do is a co-current operation, the nomenclatures are same, but the flow is different. In this case, the gas and liquid both are entering at the bottom and it is exiting at the top. So, if we do the mole balance, we will get the similar equations, and if we rearrange them, we will get y 1 minus y 2 divided by x 1 minus x 2 is equal to minus L s by G s. The slope over here is negative. Similarly, any concentration inside the column, we can write capital Y 1 minus capital Y divided by x 1 minus capital X would be equal to minus L s by G s. So, these equations of straight line with a slope of minus L s by G s, the operating line for counter current operation. So, for operating line for counter current operation, the slope will be negative, and we can just plot them, and you can see that if the mass transfer from the gas phase to the liquid phase happens, the slope of the operating line is negative. So, it is the slope, the curve will look like straight line. It is a straight line because it is based on the mole ratio unit capital Y and capital Y x. So, this is the curve look like, and similarly for the mass transfer from the gas phase to the liquid phase, So, then the operating line will lie below the equilibrium line, as it is in case of counter current operation, but in this case the slope is also negative. So, the curve will, operating line curve will look like this. Now, we have to consider, say, two systems we have considered. One is counter current operation, another is co-current operation. Among these two, which one is best for the for the operation, or which would be economical? So, in a given situation, you can see the average mass transfer driving force is larger for counter current operation than co-current, because in case of co-current you can see the operating line equation, as it is reaching closer to the equilibrium line, the driving force is gradually decreasing. So, the amount of solute transfer using a given amount of solvent is much greater in case of the counter current compared to the co-current mode. Thus, for the same equipment size, smaller flow, or for same flow rates, smaller equipment size, hence counter current contact is preferred over co-current operation. So, for the same equipment size, if we take, we need to have smaller flow rate to complete the specific job, and for the same flow rates we need smaller equipment size to complete the same job in case of the counter current operation compared to the co-current. Hence, counter current contact is much preferred over the co-current operation. Thank you for hearing this lecture, and we will continue with our interface mass transfer topic in our next lecture.